Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 32, we will learn about machine learning workflow via linear regression, and that's also in Python. So the different concepts that we will cover will remind you about the machine learning workflow, which we did earlier. And then we'll talk about linear regression using a linear regression problem in Python. We will talk about developing multiple models in parallel. We will do multi-collinearity checks. We will look into the correlation matrix and then decide how should we go ahead or not with different variables or different features. Then we will look into the scikit-learn pipeline. We will learn about the concept of pipeline. We will look into the concepts of cross-validation, which help us in generalization. Then we will look into predictions and model comparison. And then we will look into the concept of learning curve. And finally, the concept of spatial generalization. So, just to remind you, when we discussed that in the last lecture, we have developed a machine learning linear regression problem, right? We are going to do the same exact problem again in linear regression, but in a little bit different way. And what's the different way? Now, just running code and getting a result by running a machine learning model is not a big problem. It's very easy, right? So there is not much, and in today's context, we can generate code using any kind of AI tools, and that actually we just need to interpret that, and we need to modify certain things. But question is, if I really want to build a machine learning model which is be used for prediction, I need to consider many things. That means I need to go step by step and then only build the model. If I make some mistakes in between, then the model may not be that good. Even though accuracy is good, the interpretability may be low, or maybe the accuracy is good, but it is overfitting. So many problems arises, right? So whenever we are developing a machine learning algorithm, or rather a machine learning model, we follow certain steps. So what are those steps? First, of course, define the problem, that what we are trying to solve. What is the reason we are trying to solve it, right? What are the things who are the stakeholders? What are the features which we are going to talk about, right? Which are the, we are trying to predict, right? What is its unit? All these things matter. Then of course, we have to look into the problem, how it has been dealt by others. So what is the what literature is there, right? What others are talking about it. So we have to build the theory, and sometimes what happens, maybe there is not too much work done, then we have to also use our domain knowledge in that particular field, and also we have to use our intuition to say that, well, these are the things which are actually resulting in this. That means these are the cause of this, right? So we are trying to find causation, right? Not only covariance or collinearity. So now we are trying to find cause, right? What is causing what, and we are trying to justify that with statistical analysis. So we also form hypotheses accordingly, like this is the result, that is why this is influencing this. So it could be a null hypothesis you can frame, and then, for example, traffic is related with pollution. So this we have discussed earlier as well. So that means there is a relation between traffic and pollution. So that's my null hypothesis, right? Now, once we have done that, we have to collect the data using, from wherever your source is. It could be secondary sources, it could be primary surveys, or it could be using APIs from other websites. And then once we get the data, before we do anything, we have to do some basic checks, like are there missing values, is there noise in the data, is there some measurement error. So those basic checks has to be done. Some amount of checks of our missing values and all could be done in the code itself, but even before we start writing code, or when we are forming the tables, we should do some basic checks. So that is what it's all about. Then we do data processing, that means we clean the data, we remove some outliers, we can do scaling, that means again we can do that inside the code itself, we can write the Python code so that we can do scaling and all. The reason why we do scaling, we have already discussed it earlier, that we want to normalize the variable so that effect of one variable is not too much. That means suppose the units are different, right? Suppose we are using different predictors, each has got different units. One could be in hundreds or thousands, other could be in decimals. How to bring them all together, right? So that is where we need to normalize. So this scaling is all about normalization. And then once we have done that, then the next step is to, now that we have data set, we need to divide the data set into train and split. That means train and test. So accordingly we will split the data set. The most common is 70-30 split, but obviously you can go for 80-20 as well. Now what it means is we will train the model based on 70% of the data, and the rest we can take the developed model and can use it on the remaining 30% of data, and then we find that how is the result coming. We can predict probabilities, we can define classes, we can predict classes, and then we can compare, right? So some measures of comparison are this that we have already to certain extent we will learn about those things, how we can compare that. It could be different forms of accuracy scores, or there is something called precision, recall, F1 score. So this we will learn gradually, right? Over in case of linear regression, we use R square, right? R square is one, this least square error, that is the one we will use. So model, then what we do is we select the right model, that means based on the assumptions like what kind of is it a normal, the data is normally distributed, what is the residuals, the distribution of residuals, then depending on the scatter plots, how the is it linearly, the predictor and the target variable is related. Based on all these things we decide what sort of algorithm we are going to use, right? So of course in this example we are going to use linear regression, but we obviously the choice of the algorithm depends on the nature of the data. Then feature selection, what predictors we are going to select, so that's the next step. So sometimes we can use statistical procedure as well to see which are correlated, if there is multi-collinearity, or if some so those could be the test that we can do to see if we need to select a feature or not, if we should keep it in the model or not. And sometimes it is based on theory as well, that what features are relevant for this particular predicting this particular target. So then we train the model, and once we train the model, we learn the parameters from the data. Maybe in linear regression we will learn the beta 0, beta 1 values, which are the weights or the importance of those parameters. We will estimate those coefficients, right? And then we will use this model to predict for new data. That is, maybe here we have kept 30% data and we can predict. And once we predict, then we can have this R square and root mean square error, these matrices, to evaluate what is the difference between actual and predicted data, right? And interpretation of results has to be done after that. That means that which is positive, when which coefficient is positive, what is the direction of that coefficient, what is the weight of that coefficient. So those would be the things that we will analyze, and we can determine that which policies will work to change the outcome and so on. And then finally we also do, before interpretation, of course, before when we are building the model, we do validation and generalization as well. This could be of different ways of validating and generalizing. So sometimes we validate by taking a method by dividing the data set into random. We pick up random samples from the data, and we can train the model on that, and we can see how it performs over the different sessions of training, or in different cases of training, and then we can see if those are all fine, the standard deviation is not much among the R square scores, then that's a it's a general model, right? If the model is generalized. Sometimes we can go for spatial generalization. That means, does the model works in all areas separately, spatial areas. It could be also based on like how much amount of data, that if I can change the amount of data, does the R square value changes? So all this could be ways to test that model further. Then finally, once the model, we are satisfied with the model and all, we have to deploy that for making decisions. So we will explain all this using the example of a the Python program for linear regression. We exact same program we did earlier, but we now will do it in more detail. The first parts remain as it is. We import pandas PD, numpy np, and we from sklearn we import train test split, cross val scores, cross validation score. Then we import something called a pipeline. We will learn about this. Then we will import standard scaler, which help us to scale the data, numeric data, and then simple imputer help us to change, fill up the empty spaces by taking the median value or average values. And then we are importing linear regression in the model, and we are also importing the metrics R square, R square score, and mean squared error and mean absolute error. These are the three measures. We know all these measures earlier. We have done those, and we will, these are the three measures that we will use to compare. So from sklearn.model selection import learning curve. So this is something which we will also introduce over in this particular lecture, the concept of learning curve. And also we can from statsmodel.api we can import SN, and from statsmodel.stats.outliers_influence import, what we can do is we can import variance inflation factor. So VIF can be done. So VIF is variation inflation factor. We will learn about that. It is used to test multicollinearity. And then we are also importing plots over here from matplotlib, and so that we can generate plots. And the first we are loading the dataset tripgen model underscore reduced to to the data frame over here df, and then we are printing its path, we are printing its shape, we are listing the columns, and also we are printing the first 5 lines of the data from first 5 rows of the data. So over here it is the file name, this is the shape of the data set, 258 rows, 11 variables, and columns. These are the name of those columns that are given. So if you remember the model that we talked about earlier, we were predicting total trips generated, and we could use, instead of we have total population for that particular area, we have male population, female population, area of residences, area of commercial. So these are land uses, then floor area of residential, floor area of commercial, then there is roads, then there is transit station, which are accessibility parameters, and then there is residential density and commercial density, which are interaction terms which takes into account both the area and the the floor, the land area and the floor area, right? So this is floor area divided by area is the density over here. And then finally these are the 5 rows of data. Of course, not all columns are given, so, and then 5 rows and 11 columns are written. These are not shown. The dots indicate there are other columns in between. So what we are doing is we are first defining the models. The target variable remains same, but we will change the features in the model, right? So the core population is both population M and population F, and core access, this group of variables are AR roads, transit station. So these are the accessibility values, these are the population values, right? So this two remains same. What we change is in case of features, we can say that we keep core pop, core access, but we change AR resi, AR com. So we are taking only the land use features. Or we can, in model A, you can say in model A we are keeping land use, in model B we are taking the floor areas, and in model C we are taking density. We are now trying to see which model will perform better. That means which selection of features will give us better results, right? So once we have done that, so we can print those as well. So that is what we are doing, and we are also checking some values, like with this particular statement we are checking that okay, how many values are missing, and then we are also counting them and printing them as well. So over here you can see we are printing the 3 models, what we have done, what we are what we have put in here itself, and then we are also showing where are the missing values. So we see there is 1 missing value for transit station, and then there are 4 for residential density and 1 for commercial density. So the next thing that we do is multi-collinearity check. You already know why we do that. we see that if there are some variables related with each other, because actually if both of those variables are put in the model, it will have a bad influence on the sign. That means it may have unstable influence on the sign. So in some so it is prudent not to keep both the variables, or convert them using an interaction term by combining those two, or remove one and keep the one which is more dominant or more important, right? So we can first we are printing the summary, we are also printing the target variables, and so the target is total trips generated, the summary is count, mean, standard deviation of all these trips generated, right? Minimum value, 25 percentile value, 50 percentile value, the max value, and so on. So we are having a summary of this total trips generated, that is being printed over here. Then what we are doing is we are generating the correlations of the different features with the target variable, of course, and also we are sorting them. So first we are calculating the correlation over here, correlation numeric only, and then we are also sorting them, and then parallelly we are printing all this. So you can see over here we are printing both the features over here, print the features from this side, and the correlations as well, which is over here. And you can see the total trips generated would be obviously correlated, the value would be 1 because it is correlated to itself. For everything else we can see the correlation values, right? So all are positive, only one transit station is negative. That means the far away I go from the transit station, less number of trips would be generated. So that's the correlation check. But what we are not able to do is this is not multi-collinearity. So for multi-collinearity we introduce something called VIF. So model. So what we see is for VIF, it is known as a variance. It's a VIF measures how strongly each predictor is explained by the others. So what VIF does is it takes, suppose these are the predictor variables, right? We take population name. Now I see how VIF is related with the other variables, right? If it is correlated with the other variables, then and then I can take a measure called VIF, which combines all the correlations with the other variables using, and then it can give a score for that. And we already have covered that earlier. So what we see is for each of this variable, for each of these three models we check the VIF values, and you can see the VIF scores of each of this, right? That means for each three models that we are generating, that is happening over here for all the different models, we are taking each variable and computing its VIF score in reference to the other feature variables in that particular model. And accordingly, once we do that, we get these three tables, and we can easily say that model C has got lower VIF, so it has got less structural multicollinearity, and probably we should go for model C. So this is where we determine which model is better, and or rather which variables also. From here we can determine which variables to keep or not. Sometimes we can change the selection of variables, or if the model is also because in this case we have changed features and done this three different models, we can also choose the right model as well. Then this shows us the correlation matrix of the model C, because that is the model we are choosing, and if the correlation matrix is more or less okay, then we can actually we could have done it earlier as well. So both correlation matrix as well as the VIF, this actually help us to understand multicollinearity, that is what is related with what, and we can do feature selection or model selection using both this and VIF. So over here what we have done is once we have done the VIF, we have selected model C, so we are finding the correlation matrix for model C to check if everything is fine. So we see that there is not too much of critical correlation, so we are more or less keeping all the features of the model. So how to read this graph and all we have done earlier. So we are plotting we are first finding the correlation over here, and then we are also plotting that using and the figure size is given, and this correlation matrix aspect auto ensures rows and column matches the features, and then that means how you are showing all these labels actually will match, and then so the rest is we are doing model C features, so this is being printed, and then eventually we are plt.show actually plots the image. After that, we are defining a function which is def fit eval model. This is the main function that we are defining. So over here, what we are doing is we are passing x. This is the pd.data frame, and then pd.series name, and the name names are string, and then random state 42. So what it does is we are defining a function named fit eval model with x, which is a pandas data frame of predictors, y is a pandas series of targets of the output variable, and name is a string label for the model for reporting, and random state is a fixed seed for reproducibility. So that means every time we use 42, that means we will get the same combination of same results. So what we are doing is we are fitting a standardized linear model with train test split, return matrices, and a fitted pipeline. So we will come to the concept of pipeline after this. So this is we are using train test split to split the data into 70 and 30%, and then again random state is 42, which we are passing from over here. Then we form the pipeline. So this is the first time we are coming to the concept of pipeline. Now what pipeline is it lets us put data cleaning, feature preparation, and model training together in one step. That means to ensure that there is no data leakage between the different columns, we can create a pipeline which standardizes the process which follows. So any model I generate, it follows those particular pipeline. That is, first it will impute, that is whatever is the empty data that would be empty cells that would get filled. In this case we are using median for that. Then we are scaling the data using standard scaler, and then we are calling the model linear regression within that pipeline. So that means it will always go in series. It cannot go one, if we are not doing this, sometimes we could make mistakes and so on. And once we have done that, we can, pipe.fit actually help us to fit this pipeline with this X train and Y train data. That means we are fitting the pipeline on training data, and this will result in all these steps to be done one after another, and finally we get the linear regression, and the linear regression will learn the coefficients using the X train and Y train data. Now once we have done that, we use this train model to do the prediction, pipe.predict X train and pipe.predict X test. So you can see that we are training and testing predictions. What we are doing is we are checking for overfitting now. So train predictions for training data and test predictions for test data, and then we have to compare both this train and test performance to detect if there is overfitting, right? So that means if these values of R square, RMSE, MAE, this we have to check. So now what we are doing over here is we are computing performance on the training set and computing performance on the test set, and that is R square values, RMSE values, ME values, and that we are getting from these two steps, and then and these are the three things and the comments for that. So R2 score gets the R square value, NP dot square root gets the RMSE value, mean absolute error gets the ME value. So these are returned, and then this would be stored. This matrix function returns them, and this once I pass on this train and train data, it will return these values, and it is stored over here. And similarly for Y test, pred test, it will run the model with this data, and then it will get the model for the test data, and then it will store in this particular variables. So after that, what we do is once we have got those data, that is fine. We now have got the values for this different things, but we want to run the model with cross validation. Now what is cross validation? Cross validation on training split actually results in more robust generalization. Now how it happens? Cross validation means we do 5-fold cross validation on training data. In this particular case, we have taken CV equal to 5. What it means is, so this is the cross validation function. Now what we are doing over here is, we divide the data into 5 parts, 5 folds you can say. So what it means is, it splits the data into 5 parts, and then once it does that, then we train on 4 parts and validate on 1 part, right? We repeat 5 times and return 5 R-square values, and then we can check the R-square values for their standard deviation as well as average values and so on. So cross validation provides a more reliable estimate of model generalization, because we are making the model multiple times with different combinations of data, by evaluating performance across multiple training validation splits rather than a single split. So detects overfitting and instability and provides more reliable estimate of generalization performance. So once we have done that, so now once we have finalized this, then we are using that. We are, over here we are storing all this, the model name, the shape, the R-square value, and for both train and test, rounding it till the 4 decimal points, RMSE values. And once we have done that, then we find the mean of and the standard deviation for all the R-square values that we have generated, right? So that is happening over here. And finally, we keep the rest of the things, and these objects are stored for later use. The train pipeline pipe, train test data splits for test prediction. So this we keep for later, but this is what we are able to do. That is, we are finding this, all this, we are making the structure ready so that we can call it later on, and we can generate all this, CV scores, CV mean as well as CV standard deviation. So then this is the end of the function that we defined at the beginning, return out. So now we are calling that. So that means res A fit eval model, where we are passing all the parameters that we talked earlier. So we fit and compare models, the 3 models A, B and C, and then RSA, RSB and RSC are the dictionaries returned by the fit eval model. So what it returns is given by the model, and then this would be stored in this particular dictionaries. So automatically Python will choose, it's a variable dictionary, whatever it is, according to the return data, it will store it over there. So the first model is of course the model for land use, the other is for floor area, and the third one is for density. And we are now going to compare these particular models, and for R in RS, RSB and RSC, we are going to we are running the model, and then we are storing those data. So for R in RSA, RSB, RSC, it loops through each model result one by one, and then this K, V for K, V for R items iterates through all key value pairs of model results, and if K not in this, excludes the pipe and other objects. So that means we are just going through the results and trying to store them first before printing. And then once we have stored them, we can print comparison dot sort values. So if you see, we have stored everything in comparison, and then we are we are sorting those values and we are printing them. So what we are printing, these are the values that we are printing, and it would be printed in ascending order, right? So so this is the model, and so okay. So once we do that, we get this particular values here. So that means we get 3 models, model C, model, this is based on density, this is the best possible model because R-square values are high, accordingly it is being arranged, then the land use model, and then the floor area model. So you can get the R-square values, these are the R-square values, RMSE values, and these are the MAE values, and then these are the CV R2 mean values, right? CV R2 mean values, yeah. So actual and predicted values are extracted, residuals are, then finally what we do is, once we have determined which model, then we can also use res C, this is the the last model, and we can run it on the test data, we can predict the test data, and then we can also predict the residuals by saying that this is the actual test values and these are the predicted test values, right? So then we can also have stored those values in the residuals. Then I can plot this figure. Now what it does is, that means it actually plots. There are two plots what we are doing. So first we are doing a scatter plot, that means y test C pred test C and alpha 7. Alpha 7 is the transparency of that particular plot. So we are taking the test values and the predicted test values, and we are doing a scatter plot of those, right? So which is given over here. So actual and predicted values are extracted and residuals are computed over here, and plot.figure creates a new plotting canvas on which subsequent plots would be drawn. So we are first creating a canvas and then we are putting the plots over there. So what we are plotting? We are plotting two things. We are first plotting the scatter matrix of between actual and predicted, and the other between residuals versus predicted data. So both of these actually help us in understanding that what is the result, is it good enough, and the residuals also allows us to test that what would be the shape of the errors and all, if those are normally distributed or so and so on. So both of these plots are generated. So this actually helps us to see the robustness of the predictions. And then we come to the concept of learning curve. So what we can also do is to test robustness of these models. We can do all these things in all sorts of machine learning models, right? So that's why I'm teaching that at the beginning. But in subsequent lectures, I may not be following all these particular steps. The reason is it is up to you. That means for learning it is not required, but if you really want to design or develop a model and implement it, then these are all required. So over here, when we are doing learning curve, that means it shows how the model performance changes as the amount of training data is increased. That means we are gradually increasing the training data from 20% to 36% to 52%, 68, 84, 100. And for each fraction, we train the model and we get a R-square value. And not only the training data R-square value, we can also do cross-validation using 5-fold cross-validation, which we did earlier. And also we can plot those R-square values as well, right? So that is what we have done over here. So we have trained on X train and Y train, and so we are training using that. And then what we are doing is over here the learning curve is being called. This function is being called. We can the pipe that we will use is pipe C. Then these are the two data sets that we are going to utilize. CV cross validation will be done. Scoring is R square. The train sizes are given 0.2, 1 and 6. What it indicates is, that means from 0.2 to 0.1, that is 20% to 100%, there will be 6 equal divisions. So that is why there are 1, 2, 3, 4, 5, 6 divisions of the data. And random state again is 42. Same things will be again and again repeated. So once we have done that, then the train mean values are score mean values are detected, and that means because we are doing CV, that's why. And so for CV also we are getting the mean value for each of this number of times we are iterating. And then what we are doing is we are storing the data in this data frame. And what we do is we are now, after that, we can plot them in a curve, which is done over here. And I'm not explaining how the curve is done, because that is pretty standard. We are putting the labels and we are specifying which are the things that would be plotted. And you can see that we are plotting two things, which is the learning curve, the R square value from training data and the R square value from cross validation, right? Cross validation is where we are using both the training and the it is training data with the cross after 5-fold this cross validation, and this is the pure training data. So both of these are being plotted, and you see this cross validation is more robust. You see it gradually increases and then stabilizes. In case of R square, it is going up and down. So that means because we are using only 20% of the data or 36%, the results vary differently, right? But because we are doing cross validation, we are taking random subset of the data, it is much better, right? So this is the learning curve table output. So this whatever data you are seeing being plotted over here, this is the output which comes over here. It is somewhere, it must be, this is the print, this is where we are printing the learning curve. Now finally we are going to do spatial generalization. Obviously here we are doing it in a more rudimentary way. For example, we have a data which is both for we have a criteria which is, or a feature which is distance to transit. Now what we can say is distance to transit is a indicator of spatial difference, right? So that means there are places which are near the station, and then there are places which are far away from the station. So what we do is we take 80% of the 80 percentile of the transit distance from, we compute that first, and what we do is we divide the data set as per that. That means data which is below that we are calling near transit, data which is far away which we are calling as far from transit wards. Now once we do that, we then develop the model based on the near transit wards. Once we have developed it for the near transit wards, I am using the model to predict for the faraway transit ward, and we see that if it works perfectly, right? So that means then if it is done, then that means we are also doing spatial generalization. So it is not only by k-fold and other methods, we are also doing like spatially, if the data is coming from some other place, we can do spatial generalization as well. So this is a rudimentary way, but we could always collect data from two different station areas, or in that way also we can do. So the linear regression model is trained using only near transit wards. The trained model is then applied to predict trip generation from far from transit ward. Model performance is evaluated using R-square, RMSE and MAE, and to assess spatial generalization. And finally, we can also do a scatter plot to show what is actual versus predicted. So the more or less everything remains same. Over here you can see we are finding the distant columns quantile value 0.8, and then values lesser than quantile value would be stored over here, and far values would be stored over here, and that is using that we are trying to define the data set x near and x far, and then we can print those things as well. And once we have done, then we call the pipeline, where we are using a simple imputer to fill in the data, then standard scaler to numerically scale it, and then we are calling simple linear regression. So once we have done that, we can fit the data with x near, y near, and we can predict using the model for x far. And once we do that, we can also generate R squared scores for f y far, which is the actual values, and the predicted this y far values, or predicted far. And then same way we can do for RMSE and MAE. So this is how it shows. That means we can print the 80th percentile value, which is the 612 meter. Near zones is around 205, and far zones is around 52. 6 is the number of variables, and then spatial proxy FAR test that comes around R square is 0.7080, RMSE is 6.6, this one, and MAE is this value, right? And if I predict it, this is the scatter plot for prediction, as well as the predicted values on this side and the actual trips, which is pretty good. I will say that our R square value of 0.7 is not great, but it's pretty good. So that means it is also spatially, we can generalize this particular model. So now we have learned how to spatially generalize a model. We have also learned to normally generalize using k-fold validations and all. And then of course there is testing between train and test, and then how to select features of the model using VIF, multi-collinearity checks, scatter plots. All this we have learned in this particular lecture. So final thing that comes is how to interpret the model. So what we need to do is, once we run the models, we need to understand what are the coefficients of the model and what are those values, and we can determine the coefficients over here. For the pipe that we have created, we are running it, and then we are getting the coefficients over here, dot coefficient underscore, and we are storing the values of those coefficients over here, and standardized beta coefficient is being stored. And once we have done that, we can organize it in ascending order, and we can print those coefficients, right? And each coefficient represents the effect of one standard deviation increase in the feature on predicted trips, because we are not using absolute values, we have taken scaled values, which is based on standard scaler actually allows us to scale it as per standard deviation. So that is happening over here, right? So this is the output. You can see population M, population F. These are the different standardized beta values which we have got, and the intercept value is also being printed. And based on that, we can use this particular model also to predict for the median word, like earlier we have did in the previous lecture. And this is the result. Once we have used that to predict for the median word over here, and then we can print those data, and this is what you will see. So predicted trips for median word models using model C is 28,396 trips per day. So these are the references that we have used. And to conclude, this lecture demonstrated the complete supervised learning workflow using linear regression, showing how theory, data, optimization, validation, and interpretation come together to build reliable and generalizable predictive models for planning applications. Thank you.